So I want you to think of objects that are moving and the type of energy that they possess. Imagine a mouse on a bicycle pedaling at 10 kilometers per hour and an elephant on a bicycle pedaling at 100 kilometers per hour. That is a stupid example. I want you to imagine a mouse on a bicycle pedaling I want you to imagine a mouse on a bicycle pedaling at 10 kilometers per hour and an identical mouse on a bicycle pedaling 100 kilometers per hour. The mouse that is pedaling 100 kilometers per hour possesses more kinetic energy, and the reason why is because his speed is greater. Next, I want you to think of a mouse on a bicycle pedaling 100 kilometers per hour and an elephant on a bicycle pedaling 100 kilometers per hour. They both have the same speed, but the elephant possesses more kinetic energy because he has a larger mass. And it takes more energy to get an elephant to move at 100 kilometers per hour. So two factors affect kinetic energy, and they are mass and speed. The formula for kinetic energy is as follows. Kinetic energy is equal to mv squared divided by 2, where m is the mass in kilograms, v is the speed, in meters per second, and Ek is the kinetic energy in joules. So with this newly defined equation, we will look at sample problem number 1. Calculate the kinetic energy of a 150-gram baseball that is traveling toward home plate at a constant speed of 35 meters per second. In this question, they give us the mass of the baseball. It's 150 grams. The SI unit for mass is kilograms. So we have to express this in kilograms. Divide by 1,000. It's 0.150 kilograms. The speed of the baseball is 35 meters per second. And they want us to determine the kinetic energy. We know that Ek is equal to mv squared over 2, so 0.150 kilograms times 35 meters per second, and don't forget to square it, divided by 2. If we punch this into our calculator to 2 significant digits, we get 5 184 joules or to 2 significant digits, 180 joules. Joe, you're fired.
I never got that.
92? Okay. So if you put it in... If you punch this into your calculator, you should get 92 joules, like we did the very first time. So what's the relationship between work and energy? Well, the relationship is based on the work-energy principle. And the work-energy principle tells us that the net amount of mechanical work done on an object equals the object's change in energy. So we have this statement that summarizes the work-energy principle, and it says that the work done on an object is equal to the change in energy of the object. So I want you to remember, whenever you do work on an object, in a physical sense, what you're doing is changing its energy. In sample problem number 2, we have a 165-gram hockey puck which is being pushed by a constant force of 5 newtons for a distance of 0.50 meters. And we want to determine the puck's speed. There's not enough information to use kinematics to determine the puck's speed in this example. But there is enough energy to use the work. But there is enough information to use the work-energy principle. You have to understand it, however. You have to understand that when you apply a force over a distance, you're changing the object's energy. In this case, the work done by applying a force of 5 newtons over a distance of 0.50 meters will give the puck speed and therefore kinetic energy. So the work done is equal to the kinetic energy that you've given this puck. So let's write this statement mathematically. The work done on the puck is equal to the kinetic energy possessed by the puck. So let's find the work done at first. Work is equal to F cos theta delta D. So that's 5 newtons times the cos of 0 is 1, because the force and the displacement are in the same direction. 0.50 meters. We end up with the work done is 2.5 joules. So we can use this now. The work done is 2.5 joules, and it's equal to the kinetic energy. So 2.5 joules, we know the equation for kinetic energy is mv squared over 2. If we rearrange this equation and solve for v, the first thing we need to do is get rid of the 2 in the denominator. In order to do so, we multiply both sides by 2. Then we'll need to get rid of the m, which is in the numerator. In order to do so, we need to divide both sides by m. In order to get rid of the squared sign on the v, we'll have to take the square root of both sides. When we do all of this together, we end up with v is equal to the square root of 2 times 2.5 joules divided by m. Sub and solve. Make sure you report the mass in kilograms, 0.165 kilograms. carefully punch it into your calculator and report your answer to 2 significant digits. You end up with a speed of 5.5 meters per second. So we solved this kinematics quantity using the work energy principle. In yesterday's discussion of work, we lifted a box up a vertical distance of 0.95 meters. Today I've told you that whenever you do work on an object, you've given it energy. But if you take this box and place it up 0.95 meters, what type of energy have you given it? The box seems to be the same. The only difference is that it is above the ground. Well, any object that is above the ground possesses a special type of energy. And I want you to think of Niagara Falls as an example of this. Niagara Falls is an amazing wonder of the world, and it is basically water that is above the ground. And this water that is above the ground has energy. And the energy is realized once it starts falling. When it falls, it can be converted into kinetic energy. So it's as if it has this stored potential energy that can be used to make kinetic energy. And this stored potential energy, as a result of its height above the ground, is called gravitational potential energy. And that is the second type of energy that we will look at in today's lesson. In general, a potential energy is a form of energy that an object possesses because of its position in relation to forces in its environment. Gravitational potential energy is the energy possessed by an object due to its position relative to the surface of the Earth. Presently, I am standing on the ground, so you could say that my height is 0 if you make it relative to this ground. Horrible. Right now, I am standing on the... Presently, I am standing on the floor, so my height above the ground is 0. However, in order to get to this floor, I had to climb 2 flights of stairs. So my height above the ground is relative to where I choose my reference point, relative to the floor on the second story of this building, my height is 0. Relative to the outside, my height is 2 stories above the ground. So when you're talking about gravitational potential energy, it's important to establish your 0 point. The equation for gravitational potential energy depends on 2 factors. The first is the mass of the object, and the second is the height of the object. So the equation for gravitational potential energy is mg delta h, where m is the mass in kilograms, g is the gravitational field intensity, measured in newtons per kilogram, and delta H is the vertical displacement of the object from its reference point. we call vertical displacements height. The height is measured in meters. Let's take a look at sample problem number 1. We have a 48 kilogram student at the top of a 110 meter high drop tower ride relative to the ground. We want to determine the gravitational potential energy of this student. The mass of the student is 48 kilograms. The vertical displacement of this student is 110 meters. Since this is on Earth, we know that the gravitational field intensity is 9.8 newtons per kilogram. And we want to determine the gravitational potential energy. We can use our newly defined equation, mg delta h, sub in these values, where m is 48 kilograms, g is 9.8 newtons per kilogram, and the vertical displacement is 110 meters. We punch these values in our calculator to 2 significant digits. We get 52,000 joules. We can also write this as 52 kilojoules. And in fact, units of energy tend to be quite large, so you often see them expressed in kilojoules or megajoules